Imagine an LFP battery that can push an electric car more than 1,000 kilometers or 652 miles on a single charge. Not a concept, not a lab experiment, an actual battery already powering a production vehicle. For years, the EV industry has operated under what felt like a basic rule of physics. If you want extremely long range, you need nickel-rich lithium-ion batteries such as NMC or NCA. LFP batteries, on the other hand, have usually played a different role. Even Tesla uses them mainly in the standard range versions of the Model 3 and Model Y. They're cheaper, they last longer, and they're widely considered safer. But historically, there has always been a compromise: lower energy density and shorter driving range. So when an LFP battery was tested in a car and managed to travel 652 miles, a lot of engineers reacted with skepticism, because on paper, that number shouldn't exist. For more than a decade, EV development has followed a clear engineering logic: higher range requires higher density chemistries. Yet suddenly, an LFP battery seemed to challenge that entire assumption. So how exactly did it happen? And could this change the direction of EVs? Welcome to the channel. Great to have you with me. I'm Mike. Stick around by subscribing. There's a lot more interesting stuff coming, and my goal is 100 subscribers this week. So please help me reach that goal. Thanks. The answer appears to lie in BYD's new generation Blade Battery, a technology that already had a strong reputation even before this latest breakthrough. To understand why this result is so surprising, we need to rewind a little and look at how different battery chemistries have shaped the EV industry. For years, nickel manganese cobalt and nickel cobalt aluminum NCA batteries have been considered the gold standard for premium electric cars. The reason is simple: energy density. These chemistries allow a battery to store more electricity for the same amount of weight. And when a car can carry more energy without getting heavier, it can travel farther. That extended driving range has always been one of the key factors convincing people to switch from gasoline vehicles to electric ones. LFP batteries, by comparison, have mostly been used in budget or mid-range EVs. Their strengths are clear: lower cost, exceptional durability, and excellent thermal stability. But their biggest limitation has always been energy density. To reach the same range as an NMC battery, an LFP pack usually needs to be larger and heavier. That's why LFP has long been seen as the practical choice, but not the high-performance one. BYD set out to challenge that perception with the creation of the Blade Battery. Instead of the conventional block-shaped battery cells, BYD designed long, thin cells that resemble blades. These cells can be inserted directly into the battery pack structure without relying on multiple intermediate modules. That design change might sound simple, but it has major consequences. By eliminating many structural components that don't actually store energy, the battery pack can dedicate more space to the active materials that do. In other words, even if the chemistry itself hasn't changed dramatically, the system-level energy density increases. But BYD's latest generation appears to push the concept even further. Data from vehicles like the Denza Z9 GT suggests a driving range exceeding 1,000 kilometers under the CLTC standard, roughly 652 miles. Numbers like that used to appear only in EVs equipped with extremely large NMC battery packs, and sometimes not even in real-world driving. Interestingly, the battery pack in this car isn't unusually massive. It's around 122 kilowatt-hours. Large, yes, but not unprecedented. Several premium EVs already operate in that capacity range, which raises an obvious question: why did the range increase so dramatically? Yeah, there are three major factors. The first is overall energy efficiency. An EV's range isn't determined by the battery alone. The electric motors, power electronics, vehicle aerodynamics, weight, and energy management software all play important roles. BYD has been steadily improving the entire vehicle architecture. One example is the use of gigacasting, a manufacturing process that casts large sections of the car's frame as a single piece. This reduces the total number of parts and lowers structural weight. A lighter vehicle with a more rigid chassis uses energy more efficiently, allowing every kilowatt-hour in the battery to push the car farther. The second factor is improvements in the battery structure itself. The new Blade battery uses space far more efficiently, reducing intermediate components and increasing the percentage of energy-storing materials inside the pack. Even a modest improvement in individual cell density can translate into a much larger gain at the pack level. The third factor, and perhaps the most intriguing, is thermal management and chemistry optimization. BYD claims the energy density of the cells increased by only about 5%, yet the driving range improved by 20 to 25%. That gap has led many analysts to suspect there may be deeper changes within the materials or the battery management system that haven't been fully disclosed. If real-world testing confirms these numbers, the implications could be enormous. For years, one of the biggest concerns among potential EV buyers has been range anxiety, the fear that a battery won't last long enough for extended trips. But when an electric car can travel more than 1,000 kilometers on a single charge, that fear starts to fade. And there's another important consequence. Achieving that kind of range with LFP batteries, which are cheaper and more durable, could dramatically reshape the economics of EV production. Instead of relying on expensive materials like nickel and cobalt, manufacturers could use more affordable battery chemistries while still delivering similar performance. In a way, this illustrates a common paradox in technology. Sometimes progress doesn't come from inventing something entirely new. Sometimes it comes from perfecting a technology that already exists. If the 652-mile range of the new Blade battery already surprised the tech world, the charging performance might be even more shocking. So how fast can this battery actually charge? Search for BYD battery online, and you'll quickly see one number getting enormous attention: 5 minutes. According to the company's data, the new Blade battery can charge from 10% to 70% in about 5 minutes. Under normal temperatures, it can go from 10% to 97% in just over 9 minutes. For years, manufacturers have been working to reduce charging times to under 20 minutes for a 10 to 80% charge. BYD, however, is aiming for something very different: nearly a full charge in under 10 minutes. To achieve that, the company is developing 1,500 kilowatt ultra-fast charging stations. For context, most DC fast chargers today deliver somewhere between 150 and 350 kilowatts. Some experimental systems are approaching 500 kilowatts, but 1,500 kilowatts represents a massive leap. Of course, charging speed isn't determined only by the charger. The battery itself must be able to safely accept that much current. If a typical battery is charged too quickly, heat builds up rapidly. That heat can degrade the battery over time or even create safety risks. So reaching these charging speeds required improvements across multiple areas: electrode materials, cell design, battery management software, and cooling systems. The blade-shaped cell structure may play a key role here as well. Because the cells are long and thin, heat can dissipate more evenly compared with traditional cylindrical or prismatic cells. When huge electrical currents flow through the battery during fast charging, the heat spreads across a larger surface area. That reduces the risk of hotspots, one of the main causes of battery degradation. But perhaps the most surprising performance appears in extreme cold. In one test, the new Blade battery reportedly charged from 20% to 97% in about 12 minutes at minus 30 degrees Celsius. Many EVs even limit fast charging in cold weather to protect the battery cells. At around minus 20 degrees Celsius, some vehicles need to preheat the battery before fast charging can begin. That process alone can add a significant delay. So a battery pack that can nearly fully charge at minus 30 degrees Celsius and do so only a few minutes slower than at room temperature is extremely unusual. This suggests BYD may have made substantial advances in thermal management and electrode design.